Okay, so first lecture is mainly with the Taylor series. Okay, this is the topic of this lecture. Let I first recall some known formula for basic derivatives. So the derivative of the power function x n is nxn minus 1. For example, the derivative of x to the 5 is 5x4. The derivative of sine is cosine. The derivative of cosine is minus sine. The derivative of ln x is 1 over x. And the derivative of exponential x is exponential x. You all must know this formula. So we need this formula to define what we call the Taylor series. So what's a Taylor series? A Taylor series is used to represent a function as an infinite sum of terms, and Taylor polynomial just taken first n terms of the Taylor series. Okay, so it's a polynomial. This is the formula for the Taylor polynomial. This is the definition. It's a sum for 0 to n of the kth derivative of f at x0 divided by factorial k times x minus x0 to the power k. So here the variable is x, and these are non-negative integer exponents. So this is a polynomial. This is a polynomial function of degree n. So this is the highest degree of this polynomial. And this is the Taylor polynomial in the neighborhood of this point x0. Okay, close to x0, close to this point. Okay, so we'll see why do we need this Taylor polynomial, because we'll see that it can be a good approximation of the function f. So when the function f is complicated, okay, we replace f by this polynomial to do some calculations. Okay, because calculating the integral of a polynomial is more easier than the integral, for example, of some complicated functions. Okay, so in this formula, this is the kth derivative at x0. Of course, must exist to calculate the Taylor polynomial of f. Okay, and this will be the coefficients of the Taylor polynomial. So depending on n, the degree of the polynomial, so we'll have different approximation of f. Of course, theoretically, adding more and more terms will improve the approximation. So we'll discuss this later. So for example, the Taylor polynomial of f in the neighborhood of x0 of order 0, polynomial of order 0, this is a constant. It's just the value of f at x0. The Taylor polynomial of degree 1, t1, we add a term which is the first derivative of f x0 times x minus x0. T2, it's t1 plus the term of degree 2, it is the second derivative at x0 by 2 factorial x minus x0 square, and so on, degree 3, and we can go further, degree 4, degree 5, Okay, so degree 4, we have to reach the fourth derivative of f at x0 times factorial 4 x minus x0 to the 4. So as I told you, the purpose is to express complex function as a sum of polynomials. Okay, so this is an approximation. We approximate our function f by a polynomial in the neighborhood of some interesting values of x. So this is, for example, a link. So you can go to this web page and have a quick summary about Taylor polynomial. Okay, and you'll have also video here about an example how to calculate Taylor polynomial of exponential x and ln x near 0 and sin x near a equal pi over 4. Taylor polynomial of these functions. Here, just let's say that the concept of Taylor polynomial is an extension of the concept of linearization. Okay, so here, if you take, for example, so here, if we see the Taylor polynomial of degree 1, so we can see that f of x is f of x0 plus f prime x0 x minus x0. Okay, so this is the equation of the tangent line to the function f at the point x0, f of x0. Okay, the tangent line to the graph of the function at this point. This is the equation of this line. Polynomial of degree 1. The graph of polynomial of degree 1 is a line. Okay, and this is called the linearization. We replace f by a linear function. This is a linear function, a polynomial of degree 1. Okay, but we can, of course, go further and improve the approximation. Let's see an example. Okay, I'll calculate an approximate value of sine of 0.5 using a Taylor polynomial of degree 5. Okay, so how to calculate sine half. So what is the formula? Here we need T5. So what's the formula for T5 of x? T5 is fx0, the 0, plus f prime x0, x minus x0, plus f double prime x0 factorial 2 x minus x0 square, plus the third derivative of f x0 3 factorial x minus x0 cube, plus the fourth derivative at x0. Always evaluate the derivative at x0. It's not f prime of x. It's f prime of x0. X minus x0 4 plus the fifth derivative factorial 5 x minus x0 to the 5. Okay, so here to calculate the Taylor polynomial of degree 5 approximating this function at the point 0, 5, we need to calculate the derivative of the function f till the first order. Okay, we need to have till the fifth order derivatives. Okay? So this is the formula of T5. Okay? At a point x0. So the question, which point x0 will we choose? We choose a point close to 0.5. Okay? We can choose x0 equal 0. Can choose x0 equal 1. We can choose x0 equal can we choose x0 equal 0.5? Here we cannot because we want to calculate f of 0.5. Okay? So ما نعرفها هذه. We don't have a calculator. We want to have it to calculate it analytically. F of 1, we don't know which values we can. So here in the slides, he choose to calculate to take x0 equals 0. So this is easy. So what we have to do is to calculate the derivative of the function. So fx is sine x. So what is the first derivative? What is the derivative of sine x?
0.
No. What is the derivative of sine x?
Cosine.
Now, what is the derivative of cosine?
Minus sine.
What is the third derivative? So what is the derivative of minus sine? It's minus, and the derivative of sine قلنا cosine. So minus cosine. What is the fourth derivative? It's minus sine. So it's sine x. And finally, what is the fifth derivative? It's cosine x. And now we are good. So here, f prime, it's not minus cosine, it's cosine of 0. What's the value of cosine of 0?
1.
What is the second derivative? Minus sine of 0.
0.
What is the third derivative? Minus cosine of 0.
Minus 1.
The fourth. Sine
0.
of 0. And finally, the fifth. Cosine 0 is
1.
okay. So if we replace here in this formula, now we are done. So f of x0 is 0. F prime is 1 times x minus x0 قلنا is 0. Plus f double prime is 0. F third derivative 1 minus 1 x cube 0 and 1 over 5 factorial x. Okay, so T5 here, the approximation of f of x in the neighborhood of x0 equals 0 is x minus 1 over factorial 3, so 6 x cube plus 1 of factorial 5. Factorial 5 is 120 x5. It's a polynomial of degree, polynomial, only a whole number exponent of x. So polynomial of degree less than or equal 5. If you want T6, for example, if you want to go till T6, we have to calculate the 6, the derivative of order 6. But what is the derivative for the 6 will be minus sign, and evaluated at 0, it will give 0. Okay? So here, T6 also will be the same for this function. Huh? T6 or T5 will give the same Taylor polynomial. Okay? So this is the Taylor polynomial. But what is our original aim is to calculate an approximation of sine 0.5. So sine 0.5, it's f of 0.5. And the value of f of 0.5 is approximately equal to T5 of 0.5. So it's 0.5 minus 1 over 6.5 cube plus 1 over 120.5 to the power 5. Okay? Can you calculate this value? Okay, it's calculated here. You can check. So these are action and this derivative. These are the coefficients. This is T5. This is the final expression of T5. And T5 of 0.5 is approximately equal to 0.48 here. We can check what is sine 0.5 with the calculator. Okay, so here, of course, the angle is in radian. So sine 0.5 is, if we want to be more precise, 4794255.386. Okay. Here, T5 of 0.5, it's 0.48177. Okay, so at 0.5, the Taylor polynomial of degree 5 give me an approximation of the function f up to 10 minus 2. Okay, 2 digits after the, so it's an approximation of order 10 minus 2. Badin, is it fine with you, the quality of the approximation, or you need a more precise result? Okay, you need a more precise result. You will need more terms in Taylor series, so you have to go to higher Taylor polynomial degree. Okay, you have to try the order 7. Example, so here it's easy. So T7 of x will be x minus 1 over 6x cubed plus 120 x5 minus 1 over factorial 7 x7. Okay, so this is T7. And if you calculate T7 of 0.5, you will have a better approximation. You'll have something closer to 0.4794 than T5 of x. Okay, you can check it. Just remove this from this value and you will obtain a better approximation. So graphically, this is what happens. So let's see here, we have the point 0. This is the graph of the function sine x. So you know all the graph of sine x. Okay, sinusoidal function, periodic. And here the different sum of some approximation. So T1, polynomial degree, Taylor polynomial of degree 1. It's an equation of a line. So here you see that you have a good approximation in this neighborhood. Okay, so here you will have a good approximation of the function sine by a polynomial of degree 1 close to 0. If we need a larger interval, we increase the degree of t. For example, here in green, we have t3. So this is the graph of t3, the cubic function. And you see that your approximation goes till here. So here, we can say that in this interval, we have a quite good approximation of my original function sine x. Okay, the t5, it goes till here. Okay, so we improve, add in terms. So considering a higher order approximation, of course, improve, but we have to manage. We have to find a balance between the cost of the approximation and the quality of the approximation, depending on your needs. Okay, for example, T7, the graph of T7 matches the graph of sine till this. So more better approximation and larger neighborhood. Okay, so here we have a better approximation by T7. Okay, so here instead of calculating T7 إذا وقفنا في T1 مثلا بتشوف إذا وقفنا في T1 of X قلنا T1 هو X. Okay, فكم f of 0.5 if we approximate it by T1 of 0.5 هي راح تكون 0.5. So 0.5 instead of 0.48, of course, it's not a good approximation. It's a better approximation by T5 up to 2 digits. Okay. So this is the idea behind Taylor polynomial. Now, what about Taylor series? Taylor series, you take all the terms till infinity. Okay, don't stop at 5 or 15 or 20. You take theoretically, you go till infinity. You take all terms. Okay, in the you take k from 0 to infinity, all whole numbers. Okay, but what happens in this case if your function is regular? See infinity, you can derive infinitely. You will have that T infinity, the Taylor series matches your function exactly, equal. Okay, so any function equals exactly its Taylor series. Okay, so if you take all terms, infinite number of terms, you will match the function f مهما كانت your function. Okay, but هذا theoretically, of course, in the application numerically we cannot go to infinity. Okay, مش راح نبقى طول الدار واحنا نحسب. We have to stop somewhere, so we'll have a stopping criteria when you achieve a given number of iteration or a given error bound. Okay. So to conclude, the Taylor polynomial is similar to f in a neighborhood around x0, close to x0. What is a neighborhood? Of course, this depends on the quality of your approximation. We can approximate any function by Taylor polynomial. And as I told you, for example, instead of calculating the integral of exponential x1 plus ln x over x square root x cubed minus 1, this horrible function, for example, between 1 and 2, the idea is to determine some Taylor polynomial. Okay, approximating this function and integrate the polynomial instead of integrating this function. This is the idea. The Taylor series, so if you go to infinity, it's still a polynomial, infinite number of terms, and in this case, it is exactly equal to the function. Okay, but this is a theory. As I told you, in practice, we never go to infinity. So question, if we have a polynomial, if our function is already a polynomial, what is the Taylor polynomial approximation of a polynomial itself? Okay. This is just to understand, because if it's polynomial, it's easy, so no need to calculate its Taylor polynomial. But just to understand, to give you an insight about this function. So he's asking for Taylor polynomials approximation of f in the neighborhood of x0 equals 1. Okay, so what is t0? T0 is nothing else than f of x0. It's a constant polynomial. So here it's x0 power 4. x0 is 1, f of 1. So it's 1. So t0 of x is the constant polynomial. t0 of x equals 1. So it's this polynomial. Okay, what is t1? T1 is f of x0 plus f prime x minus x0. So at 1, so we need, on f of 1 is 1. We need f prime of x. What is f prime of x?
4x
4x
times x to the
cubed.
power 3.
4x cubed. So what is f prime at 1? The value of f prime at 1?
4.
It's 4. So here we'll have f of x0 here 1 plus f prime of x0 here 4 times x minus 1. So this is a polynomial of degree 1. It's 4x minus 3. Okay, so it's an approximation of x4. It's not x4. Because our function is a polynomial of degree 4, we approximated by a polynomial of degree 1. Okay, what is T2? So T2 is T1, if you want, plus an extra term, which is the second derivative over at x0 over 2 factorial x minus x0 square. So it's 4x minus 3 plus, what is the second derivative of f?
Twelve x cube
No.
square.
So you multiply by 3 and you reduce the power by 1. N minus 1. This is the derivative of a power function. So what is f double prime of 1?
12.
It's 12. So here 12 over 2 factorial x minus 1 square. What is T3? Is T2 plus, and we add the term, the third derivative. Okay, what is the third derivative here?
$24.
24x. What is the third derivative evaluated at 1?
24.
So here we'll have this polynomial. And we have an extra term, 24 over 3 factorial x minus 1 cube. And so on. And what do we notice if we make the simplification here? So here are the calculations. So first we need the derivative. So here we notice that the fourth derivative is 24, and then all higher derivative, the derivative of 24 is 0. So all higher derivative of order 5 and higher, it's 0 because it's a polynomial of degree 4. Okay? And we notice also that, so this is T0 as we calculated it, T1, T2 after simplification, T3 after simplification. So this is approximating x4 around x0 equal 1, in the neighborhood of the point x0 equal 1. What is T4? We see that T4 is f. So the best approximation of x to the power 4 by a polynomial of degree 4 is itself. Okay? And all higher approximation will be the original function f. Okay? Since f is a polynomial of degree 4. Okay? But if the degree is less than 4, of course, we'll have this polynomial as a approximation of x4. Okay? But if you want to approximate a polynomial of degree 10 by a polynomial of degree 20, it will be the original function, the best approximation. So this is graphically what it happened. This is the function x4. So this is T0, when T0 is 1, it's a constant function. So here you see it's not at all a good approximation. They match only at the point x0 equal 1. This is the approximation of degree 1, the linearization. So here, bit better. So here we have a good approximation in small neighborhood, and increasing the number of terms in the Taylor polynomial, increasing the quality of approximation. So we improve it. So here degree 3, we have a better approximation, and from degree 4 here we match. Okay, we have the exact function. But as I told you, the question, how many terms shall we calculate? And this is why when you approximate the function, you have several options, several approximation method, depending on the quality of the approximation, on the degree of for example, if you use Taylor polynomial to approximate the function, what is the degree of the chosen Taylor polynomial? Okay, it's not the only way to approximate a function, but it's one of the most used ways. So this is another example. If you want to approximate the function fx equals sine x plus cosine x. at x0 equals 0. And we want to find the Taylor series here. So Taylor series means we need all terms, T empty. Okay? So we have to calculate all derivatives. Okay? But as I said previously, with sin x, for this type of function, we can see that calculating so if f for k, if for derivative of order 4, of order 8, of order 12 is the same as the value of f. The derivative of order 5, sorry, 9, and so on is same as f prime. Order 6, same as f double prime. And order 7, 11, 15 are same as the third derivative. Okay, so we'll have 1, 1, minus 1, minus 1, and then repeat 1, 1, minus 1, minus 1, 1, 1, minus 1, minus 1, and so on. So here the Taylor series, what we'll have 1, 1, so 1 plus x minus 1 over 2x squared minus 1 over 3 factorial x4 plus plus minus minus and so on. So and we can split here even powers, odd powers, and we'll have this mathematical formula. So as I said, graphically, taken more and more higher and higher degree, we improve the quality of the approximation. Okay, so this was a main point about Taylor series. So you can take functions, easy function, and try to practice and to calculate the Taylor polynomials of a given degree of this function. Let's go back now to some derivative rules. So these are important to know. The derivative of the basic function. So now the derivative of sum of two functions is the sum of the derivatives. For example, what is the derivative of this function? What is h prime? مين يقول لي؟ Who can derivate this function?
28.
It's 7 times 4x cubed plus 2 times 2x. It's 2 minus 1. 4 minus 1. So it's 28x cubed plus 4x. Okay, this is the sum rule. We have the product rule. The derivative of the product is f prime g plus fg prime. For example, here, what is the derivative h prime? So first we derivate sine. We multiply by ln plus we keep sine and we derivate ln. So what is the derivative of sine x? شفناها اليوم.
cosine x
Cosine x times ln x plus sine x. What is the derivative of ln x?
1 over x, maybe?
1 over x. Okay. I don't satisfy with maybe. I want you to be sure about your results. Okay. but this will come with practice. We have the quotient rule, the derivative of quotient. So this is the formula. Now f prime g minus fg prime, can add a plus and a minus, divided by g square. So this is an example. What is the derivative of h? So it's the derivative of ln times x square minus ln times the derivative of x square divided by x square all squared. So it's what is the derivative of ln x?
One over x.
It's x square minus ln x. What is the derivative of x square?
2x.
Over x4. And you can simplify if you want. X square over x is x minus 2x ln x over x4. And here, if you want, you can simplify x common factor. So finally, it's 1 minus 2 ln x over x cube. This is the derivative of the quotient. Try to repeat it to get used to this type of calculation. Finally, the last very important formula is the chain rule. If you have a composition of two functions, g or f of x, the derivative is g prime evaluated at f times f prime. This is called the chain rule. Very important formula. Let's see an example about the chain rule. For example, if you want to derive 2x plus 1 to the power 4. So here, this is the composition of two functions. F of x here inside here 2x plus 1 and g of x here the fourth power. So what is the derivative of h prime? We derivate the power function. So 4 2x plus 1 power 4 minus 1 and times the derivative of the expression inside. Prime. This is 4 2x plus 1 cube times 2. So finally it's 8 2x plus 1 cube. This is called the chain rule. Okay, for a composition of functions. You have already studied that. Just try to refresh. Okay, so last example. We'll finish this first lecture. Just an application on the calculation of the derivative. So what is the derivative here? So here we have a quotient function. So f prime, it's 1 prime times 1 plus exponential minus x minus 1 times the derivative of 1 plus e minus x over 1 plus e minus x prime square, sorry. Derivative of 1, come. What is the derivative of 1? Who can tell me?
0.
It's 0, it's constant. So هذا كله 0. Minus 1 times, what is the derivative of 1 plus e minus x? Okay, misses. So this is 0 راح. هذا 1 times راح. So now we need to derive this function. What is the derivative of 1 plus e minus x? Is derivative of 1 اللي هي 0 plus what is the derivative of e minus x?
I think same.
No, it's not the same. The derivative of exponential is the same, but this is a composition times the derivative of the minus x. Okay? So finally, it's minus e minus x times minus 1. I'm going step by step. So it's e minus x over 1 plus e minus x squared. So the derivative of e minus x, be careful here, the derivative of minus x times e minus x. So it's minus e minus. So the derivative of exponential of any function is f prime times exponential f of x using the chain rule. Did you get it? So this is how it works with details, and this is the final result.